Welcome back, everyone. Today, we're going to continue with elliptic curves. So previously, we've talked about elliptic curves over arbitrary fields, over arbitrary, perfect fields. Okay, that was subchapter 3. Then we started talking about elliptic curves over finite fields. We discussed very little about elliptic curves over finite fields. We talked about the Hasse bound mostly. And then we talked about elliptic curves over the complex numbers. And then the next step is trying to understand elliptic curves over local fields. So if you haven't seen local fields, we almost constructed a local field when we talked about inverse limits. So when we described the p-adic integers, the inverse limit of z mod p to the n, which remember is just coherent sequences of classes modulo p to the n, such that when you reduce one to a lower power of p to the n, a lower power of p, then they coincide, that congruence coincides. So that's what I mean by coherent. And if you construct the field of fractions of the p-adic integers, so it turns out the only thing that is not invertible here are numbers that are 0 modulo p. So numbers that are multiples of p. In the p-adics, those are not invertible. So you actually just have to invert p to get a field. So if you invert p, then you get what we call the field of p-adic numbers, the p-adic rationals, or the p-adics. And that is an example of prototype of what's a local field. In fact, local fields are, well, any extensions, the extensions of QP, finite extensions of QP, the reals, the complex numbers, power series with coefficients in a finite field. Those are other examples of local fields. But if you think about QP, whenever I say local field, that's enough. The property that we need about local fields is that they're complete with the p-adic norm. The p-adic norm being, if you take a number a, then you can factor it. If you take an integer a, you could factor a rational number. You can factor it as a power of p times something that is relatively prime to p, and then the norm is 1 over p to the n, or 1 over p to the p-adic valuation of that number a, with the highest power of p that divides a. Anyway, QP is complete with respect to that metric, just like the reals is complete with respect to the Euclidean metric. And that allows for well, what we're going to do in a moment. All that said, we're actually not going to start right away talking about elliptic curves over local fields today, so that is not really true. What we're going to do today is take a little detour to talk about formal groups, which is the way we are going to eventually talk about elliptic curves over local fields. So let me actually give you an explanation of what we are going to do and why we care about formal groups in terms of elliptic curves. So what we are going to do is we are going to do an expansion of an elliptic curve around the point at infinity. So what I mean by this is the following. So we are going to study addition near the origin. We're going to change variables, so we are doing addition near the point at infinity, and that's going to lead to some interesting concepts here around. Okay, so let E be given by a long Weierstrass equation. And what I want to do is talk about addition near the origin. So what I need is a change of variables that is going to put the origin, the point O, at the coordinate 0, 0. remember that this is what I get when I dehomogenize my projective equation for the elliptic curve. This is the chart x, y, 1, right? But at O, so this is when we homogenize, when this is the chart z equals 1. But at O, z equals 0. But what we can do is, since y is 1, I'm going to dehomogenize at the chart y equals 1 instead. Okay, so instead of at z equals 1, I'm going to dehomogenize at the chart y equals 1. So that is what why I'm going to do the following change of variables. Let me change my camera view here. I can see you there. So unchange variables to new variables, z variable, a little lowercase z. So this is not the capital Z, unfortunately. My capital Z's and lowercase z's are very similar. So I'm going to change to a z value that is minus x over y, and a w value that is minus 1 over y. Okay, so now O actually corresponds to the value in the ZW coordinates is going to be 0, 0. And the coordinate Z is a uniformizer at O. Okay, remember that Y had a triple pole at O, and X had a double pole at O. So X over Y has a single 0 at O, and 1 over Y has a triple 0 at O. So they both vanish at O, and Z vanishes to order 1 at O. Okay? Right. So what that means, let me write that down. Recall that the order of vanishing at O of X is minus 2. The order of vanishing at O of Y is minus 3. So the order of vanishing of this new variable Z is actually minus 2 minus 3, which is 1. So that's why it's a uniformizer. And then also the order of vanishing of 1 over Y is 3. So those two statements explain why the origin is now at the coordinate 0, 0, and the function Z is a uniformizer at O. So now this equation becomes, in the new variables, if you do the change of variables, what I get is the following: is W equals Z cubed plus A1 ZW plus A2 Z squared W plus A3 W squared plus A4 ZW squared plus A6 W cubed, if I got it right. Okay, the change of variables, I needed to divide by y instead of by z to get somewhere where I could talk about the origin, about O, and the negative signs is just so it looks pretty like this, that it is all just positive on the other side. And we have isolated a w on the left-hand side. That's important here. I'm going to call this polynomial on the right is going to be f of zw, okay? And then what we're going to do, the trick that one can do here is that formally, I'm going to start recursively substituting. You see that I have a definition of W in terms of Z and W. So what happens if I put in this definition of W for every appearance of W on the right-hand side? Then I'm going to get a new equation that should also be true. And then as I keep going, I'm going to be able to essentially eliminate the W coordinate. It's all going to be W as a function of Z. So here's what we're going to do. We're going to substitute recursively. So we get to W is W of a variable Z. Okay, so starting from W is f of ZW, the next step would be F1 of ZW is going to be f of ZW, so that's still the same function. The second step would be F1 evaluated at Z, and then W I know is f of ZW, so substitute N, and then so on and so forth. I'm going to keep substituting W by f of ZW. And the effect is that I'm going to get more terms that only have Z's, and the W is going to be pushed out to higher and higher powers of Z, okay, until at the end, in the limit, we are going to obtain the following in the limit, and we are going to formalize this in a moment. But what is going to happen is that I'm going to get that W is a power series. It actually is going to start with Z cubed. When I substitute in this W here, the entire power series, now this term is going to have a Z to the fourth, this a Z to the fifth, this a Z to the sixth, this is going to be Z to the seventh, this is going to have a Z to the 9. So I'm going to only see that the first term is Z cubed, and every other term is going to have higher powers of Z. So it actually starts with Z cubed times, and then a power series in Z with some new coefficients, which are only going to be, so these is, I can tell you what that one is. That is just A1. A2 is A1 squared plus A2. A3 is something like A1 cubed plus 2A1, A2 plus A3, and etc. So what I get is a power series now for W that belongs to, so this power series belongs to, so the coefficients are in here, they're in the ring generated by A1 through A6. That is the coefficient ring, and then these are power series in Z. Okay. So here, what we actually need to show that this actually happens, we need to show convergence, that this converges to some power series of this form, okay? And we also need, we are also going to show that this power series is a solution to the recurrence relation we set up. So that this power series satisfies this property, that I get this identity that when I evaluate in my polynomial f, w in that power series, then I actually get the power series back. Okay, so our candidate for the solution of the recurrence is the following: is the limit as m goes to infinity of those f of m's evaluated at 0. Okay, presumably what we said is that as I do that recurrence, I'm going to get higher and higher powers of all the w terms. Any appearance of a w are going to be in higher and higher terms of z. And when I evaluate at w0, I lose only some higher order terms, but like the bulk of the beginning of the series is there already. And as m goes to infinity, I should get my power series that I want. So I want to show that this thing is in the power series ring with coefficients generated over the integers on A1, A6, and power series in Z. Okay, so that is what this result is going to say, exactly that. So A thus defined, so this W is a power series in here, power series with coefficients in that rank generated by the coefficients A1 through A6. If you have the coefficients A1 through A6 are integers, then the coefficients are just the integers. But if your elliptic curve is defined over some extension of the rationals, defined over some local field itself, then whatever it is A1 through A6 are, that's where the coefficients of the power series are going to live also. Okay, so the field of definition Z adjoined A1 through A6 is the minimal ring of definition of your elliptic curve as you have defined it. The second property is that this W power series is unique. Is the unique power series with the property that it satisfies that recurrence relation exactly. Okay. And part C is that if I write A1 through A6, this ring, if I make it into a graded ring, so if you now consider for a moment these A1 through A6 to be variables themselves, okay, just forget that we're completely devoid of any base field. We are just considering A1 through A6 now as additional variables. And you make these into part of this ring with weights. With weights, I'm going to put a weight for AI to be of weight I. So X yes, so here now each one of those has a weight AI. So this is a ring with five variables: A1, A2, A3, A4, and A6. Each one has weight I. So A4 has weight 4, A6 has weight 6. Then the coefficients AN. Remember, these coefficients are the coefficients that appear here. Okay, those coefficients. The coefficients, then AN is homogeneous, is a homogeneous polynomial in the graded ring. of degree n. So now it is homogeneous in the variables a1 through a6 with the weight that we gave. So for example, a1 is supposed to be homogeneous degree 1. A1 is a variable of weight 1, so it's homogeneous degree 1. A2 is a1 squared plus a2. This is homogeneous of degree 2 because a1 has degree 1, a square has degree 2, and a2 has degree 2, so it is homogeneous. A3 is a1 cubed plus 2a1 a2 plus a3. So this has weight 3. This has weight 2 and weight 1, so it has weight 3, and this has 1 times 3, which is 3. So it is also homogeneous of degree 3. Okay? And this, by the way, is another reason why in the Weierstrass equation we call A6 A6 and not A5. Otherwise, you would have to do something like really wonky here and say that A5 has weight 6, right? So this is one of a few reasons why the variables or the coefficients of a Weierstrass equation are numbered the way they are. All right, so for the proposition, I'm actually going to prove parts A and B, and what we need is a lemma, which is none other than Hensel's lemma for polynomials. Okay, so here's a version of what's called Hensel's lemma. So let R be complete, a complete ring with respect to an ideal I. And here, if you remember, one of the constructions we did with inverse limits was construct power series as an inverse limit of rings of polynomials. This is what R is going to be, is a ring of power series here, which is complete with respect to the ideal, the maximal ideal Z. So if R are power series in Z, then the ideal generated by Z, that's the ideal I in this case. And so R is a complete ring with respect to an ideal I. F of W is going to be a polynomial with coefficients in R. Polynomial. And suppose there is some A in R such that F of A is in I to the n, is in the nth power of the ideal, and the formal derivative of that polynomial evaluated at A is a unit for some n bigger or equal to 1. Then for any alpha in R such that alpha is congruent to f prime of A modulo I, the sequence that starts with W0 is A, and then recursively define Wn plus 1 is, n is taken here, let's call it the counter M, is going to be Wm minus f of Wm over alpha. Alpha is congruent to a unit modulo I, so it is invertible. And this sequence converges to an element B in R with f of B equal to 0. So we've constructed a root of f f of w, okay, such that b is congruent to a modulo the nth power of the ideal. Moreover, if R is an integral domain, then B is unique. Okay. So now for the proposition, remember we are trying to find a solution. So here's again, let me show again what we're trying to prove. We're trying to prove these two parts of the proposition, parts A and B, that there is that this is a power series and it satisfies uniquely this property. So for the proof of that proposition, I'm just going to say that what you need is Hensel's lemma. So I'm going to pick R to be the power series ring with coefficients in this ring and power series in Z. My ideal, which this ring is complete with respect to it, is the ideal generated by Z. I'm going to pick f of w, my polynomial, to be f of zw minus w, okay? And pick a equals 0 and alpha to be minus 1. So notice, note that f prime of 0, so if I take the derivative, this is a polynomial with respect to w, okay? So if we go back to the definition of fzw, which is here, this is the this part here is the polynomial fzw. If I take the derivative with respect to w and evaluate at 0, then what do I get? F prime of 0 is a1z plus a2z squared minus 1. Okay, when you take the derivative with respect to w and evaluate at 0, and this is congruent to minus 1 modulo z, which is a unit, right? So I can take alpha to be minus 1, a to be 0, f that, and then what Hensel's lemma tells you is that there is a root, and in fact there is. So now Hensel's tells you that there is a unique power series B such that f of B is 0, and that power series will have the properties that we need. It is a root. In particular, this says that B is f of ZB. Okay. So it satisfies that property, and we have such a solution. All right. Let me, by the way, let me make a remark here. This confused me at some point. So I'm not gonna give more details about this proof, but you can construct such a solution using Hensel's lemma and then show that this is the same that the one we constructed as a limit. The one that we constructed as a limit, you can show that it satisfies this property, and through Hensel's lemma, there is a unique one with that property. So that's the one. All right. So here's a question. So suppose we have that formula. We're trying to solve this over over say QP. Okay, so so what I mean is that given Z in PZP, then when I put in, so this is just the polynomial that we had before. So W equals a polynomial. Remember that this was just a cubic in cubic in Z and W. Okay. So when I put a value of Z in PZP, then there are three options for W. So which one is? So the question here is, which of the three roots is the WZ that we're looking for? So for example, for concreteness, take E is this working? I think so. Okay. So for concreteness, take E to be y squared equals x cubed plus 1. Okay. Then the equation in WZW is W equals Z cubed plus W cubed. Okay. And let's consider, for example, over Q5. So my question is, so this becomes, if I write it as a polynomial in W that depends on Z, I'm going to give a parameter Z, and then I want to know what W is in that case. So this is the polynomial in W and Z. So now take a value of Z, which is in 5 Z5, okay, and then I can evaluate it. Then I have W cubed minus W plus 5 cubed equals 0. Now I have a polynomial in W, and this has solutions. So there's actually 3 solutions. There is a solution W, which is actually 0 modulo 5 cubed, but there is also a solution that is congruent to 1 and a solution that is congruent to minus 1. Okay. So which one of the 3 is the one that is going to be my W? So for each Z, I want a W that is given me by that power series that that Hensel was providing. So the solution is that that equation, that power series WZ that Hensel has produced was built with one condition. Was built as the Hensel's theorem solution to f of w, f of zw minus w with a equals 0. And in particular, it told me that it was one with WZ equals 0 modulo Z. Okay, and in fact, there is only one root of W cubed minus W plus 5 cubed equals 0, which is 0, congruent to 0 modulo Z modulo 5, and that's the one that we want. In fact, the 3 roots, I found them using Magma, and the 3 roots in this case the 3 roots were W1, which is Magma gives you the p-adic numbers as one large integer that satisfies as many congruence conditions as you need to be. So W1, which is 91554687625, which in the p-adic expansion looks like 0 mod 5, 0 mod 25, 0 modulo 125, and then 125, 125, and the conditions keep going. Then there was a W2, which is congruent to 6182707575751, which the conditions give you that this is 1, 1, 1, 251, 1501, etc. And a third root congruent to minus 627426244536, which starts with 4, 24, 124, 249, 1499, ... So you see that the one we really want is this one. And in fact, notice that if you go back to Hensel's lemma, Hensel's lemma tells you that there is going to be one solution, okay, that satisfies your recurrence, and that root is congruent to a modulo I to the n. Here our a is 0, this has to be 0 modulo I to the n. In here, what we found was that, in fact, Hensel's tells you that the solution is going to be 0 modulo 5 cubed, and that's what we see here, that the solution is 0 modulo 5 cubed, and then it just keeps going from there. Okay, so it's the unique solution of the 3 that has that property. Okay, so what have we done is that so what we have done is that it's starting from an elliptic curve. We changed variables to a ZW universe, where now the equation looks something like this in Z and W, and this second part with ZW. But formally, for each Z, what we constructed is a WZ. So for each Z, I can actually build a WZ such that WZ is f of ZWZ. So if I've actually constructed a point for each Z, there is now a point ZW, which is ZWZ. Okay, but only with one parameter Z, I'm building points on the elliptic curve. So this is a formal solution. This is a formal point on E, which is just given as Z. For each Z, there's a power ZWZ that gives you a point on E. Okay, and so now I can actually write So I have my power series WZ, right? Which is started with, remember, it was Z cubed 1 plus A1Z plus A2Z squared dot dot dot. But I can actually right now write an x coordinate going back to the original Weierstrass equation. I can write down what the x coordinate of that was. Remember that the x coordinate was Z over W, right? Because recall that the change of variables was that, remember that Z, with Z, was minus x over y, and W is minus 1 over y, right? So I can retrieve what is x. X is going to be Z over W, okay? And when I retrieve Z over W, well, I can write down, well, I know that my W is going to be, is a power series in Z, so I can retrieve it just from the Z coordinate. Falling over here. And I can actually now write the power series, invert the power series for W, and it turns out I get a power series for X is 1 over Z squared minus A1 over Z minus A2 minus A3Z minus A4 plus A1 A3 Z squared plus dot 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 dot. And I can retrieve the y coordinate same way. The y coordinate is minus 1 over W, which is minus 1 over WZ, which is minus 1 over Z cubed plus A1Z squared plus A2Z plus A3 plus A4 plus A1 A3 Z plus dot dot dot. Okay. So you see that before I had a formal solution to my elliptic curve in the ZW plane, but via the reverting the change of variables to back to the x and y, I can actually have a formal solution to my elliptic curve in the xy plane now, which is just given as expansions in Z. Of course, this is now a power series, so if you throw in a rational number there, this is not going to converge in general, so this doesn't work quite well. But if you're working over a complete field in Z is something in the maximal ideal, then this is going to converge to a p-adic number, and you're going to get a p-adic solution. Okay, so we're going to use this to build p-adic solutions and to study elliptic curves over local fields over the p-adics, for example. You can retrieve other things. Now this is omega. Let me write it better. Omega is going to be the invariant differential. I can also write it down. Remember that our invariant differential was dx over y. In short Weierstrass form, there's some more terms in the y in the denominator when it's we wrote it back when the invariant differential for a long Weierstrass equation, but you can write the invariant differential also as a power series. So it's going to look like this with respect to Z. And all three of these are n. You can prove that these are all n in this ring of power series with coefficients in A1 through A6. And the key thing is that the pair X, Z, Y, Z provides a formal solution to our Weierstrass form Okay, and this is a solution in in a field, in the quotient field of power series with coefficients in there. Okay, so now I have a power series ring where I can build formal solutions to my elliptic curve. In any ring where I can actually evaluate this power series and something converges and I get a number, then I'm going to get solutions that that are actual points on the elliptic curve. Okay, so now the question is, over what fields can I pick an elliptic curve over K and pick a value in K such that X, these power series, converge. And that's what you need, is a complete field, or what it's called local field. So if K is a complete local field, and we have so is a complete local field, so we're going to have so we have the ring of integers, we're going to call it R. The maximal ideal there is M, and we have that the coefficients of the elliptic curve are in that ring of integers, and I pick a value Z that is in the maximal ideal, then these power series are going to converge and give me a point. Over K. Okay, so for example here, K could be QP, and as long as, well, R, the ring of integers, would be ZP. The maximal ideal is multiples of P. So as long as you put a Z value that is a multiple of P times ZP, then this is going to converge to something. Okay. And by the way, if you have not encountered p-adics before, then I would suggest that you read Fernando Govea's p-adic numbers, which is a nice introduction to the p-adics as a reference. Okay. All right.
Can I interrupt with a quick question?
Yes, please.
So this is relevant to a point that you made on this page and also on the previous page, I believe. So what do we mean by a formal solution or a formal point on the elliptic curve?
Very good question. So by formal, I simply mean that if I take the quotient field of this, call that K, then by formal solution, I mean a point on E of K. Okay, but formal here really means that it's a power series. So that gives you as much information as a power series can give you. There's just a power series solution, and we don't know about convergence. We don't even have before this line, we don't have actual arithmetic or anything. This is just like, I'm just giving you some, the A1 through A6 could be other variables, and then the Z is a variable, and it's just in some one A1 through A6, 5 variables, and Z another variable. I'm giving you solutions in 6 variables that are formal solutions, in the sense that it's just a power series solution to your elliptic curve. Okay, so it is a field because it's a field of power series, a quotient field of a ring of power series. So there's a field, and over that field there are solutions. But this is formal in that we are really interested in solutions over the rationals and solutions over arithmetic rings, right? And this is not it. This is just a power series ring. However, what we're going to try to do is find fields where we can actually evaluate these power series to actually get points on the elliptic curve that are arithmetic, which is, for example, QP. I can evaluate there and get points over QP, and then we're going to see how far are we. We're going to create a bunch of points over QP, and then we're going to try to analyze how many do we have? Do we have them all? Or how close are we to have all the points on the elliptic curve over QP with this construction? Okay. So that's what formal means. It's just that it's a solution in power series, but you can replace formal by a solution in a field of power series. Okay, so what we have here is what we obtain is over this complete field. So remember, we have K, ring of integers R, and maximal ideal M. What I have is a map from the maximal ideal of my local field to points over K. Okay, where the map is for Z, I get a point ZW, which is the WZ, right? Or if you want, we can, if you want in those coordinates, but we can sort of forget about the ZW plane already, and what we're getting is points X and Y. Okay, for every Z in the maximal ideal, I get a point like that. What can we say? The image, by the way, so the image are points X, Y, such that X, Y minus 1 is in the maximal ideal. That's because remember that X is Z over W, and Y is minus 1 over W, so X over Y is precisely minus Z, which is in the maximal ideal. Okay, so we get those points, and in fact, we also have that this map is injective. Okay, because well, if X, which is ZW, was the same as some X prime, which is some Z prime W prime, and Y, which is minus 1 over W, was the same as some other Y prime, which is minus 1 over W prime, then this tells me that W equals W prime, and then from this equation I would get the Z equals Z prime. Okay, so it's the same value of Z. So this is actually injective. So I get an injection of the maximal ideal into the points of the elliptic curve over K, over this local field. I can actually also do addition on the ZW plane, okay? And the reason I want to do that is because I want to translate the addition on the right-hand side. So if I have a point such that X times y inverse is in the maximal ideal, I can retrieve a z value that gives me that. This goes both ways. That so this part here, the image is definitely x, y value such that x times y inverse is in the maximal ideal. And if I have a point such that x times y inverse is in the maximal ideal, the z value that corresponds to it is in the maximal ideal, and therefore it comes from something from the maximal ideal. So that is exactly the image, and that's where there is a bijection. So what I want to do is actually bring back the addition, the geometric addition on the elliptic curve. I want to bring that addition back to the maximal ideal. And so I want to do addition of 2 points. So suppose I have, I have a point P, Z1, W1, and I have a point Q, Z2, W2. I want to find, so I can find a line L that is just the line that goes through PQ, and that is going to be a line W equals lambda Z minus nu. Okay, I'm not going to find those parameters, but you can find exactly what those parameters are in terms of Z1, W1, Z2, W2. Okay, and then once you have that line, I can intersect with my elliptic curve and find the third point of intersection. So, and then find, again, with the purpose of finding what is the sum of 2 z values. Okay, so I can find the intersection. There will be z1 will be one of the points in the intersection. The point with z2 coordinate will be another point in the intersection, and then there is a z3 value, which it's the one that I'm interested in, which is the z3 that corresponds to z1 and z2. And there is a formula for it. I'm going to copy it here in terms of all the things we've seen, is minus z1 minus z2 plus a1 lambda plus a3 lambda squared minus a2 nu minus 2a4 lambda nu minus 3a6 lambda squared nu over 1 plus a2 lambda plus a4 lambda squared plus a6 lambda cubed. Okay, the formulas for lambda and nu, again, which can be just computed by the equation of the line, I'm not writing them down, but this is the z3 value of the third point of intersection between E and this line. This is, again, is a power series, or this is a now a power series in A1 through A6, and now power series in Z1 and Z2. Well, okay, and remember that the inverse point, or the point P plus Q, is the inverse of this third point of intersection. Remember that the inverse in the XY plane is given by X minus Y if it was a short Weierstrass equation. If it's long as this equation, and therefore the inverse for a Z value is going to be X over Y plus A1X Z plus A3. So this is the Z coordinate of the additive inverse of a point. And therefore, I can now compute the Z value of the sum of 2 Z values. Okay, for each Z value, I have a point on the elliptic curve. I went to the elliptic curve, did addition on the elliptic curve, and then come back and find what is the addition of 2 points. So this capital F is going to be the sum, the Z value that corresponds to the sum of 2 points on the elliptic curve and this is just a negative, the additive inverse of this of the z value that corresponds to the third point of intersection with the line. And you can, just following all this like nightmare of a recipe, you can compute that, and it turns out this is again power series in two variables, z1 and z2, and it is again a formula for the addition of 2 points. Remember that for every z value, the w value, I can compute it with my w power series. So I don't really need the w. I need to know for z1 and z2, send them over, add them, bring them back, this new z value of the sum of the 2 points, that's the one I was after, and that is what we've constructed here. Okay, so what we've built is a power series a two variable power series and with these coefficients that has the following properties, that f of z1, z2, the addition on the elliptic curve is commutative, so it should be the same that f of z2, z1. We also know that the addition on elliptic curves is associative, so f of z1 comma f of z2, z3 should be the same as f of z1, z2 comma z3. Okay, so this is because addition is commutative. This is because addition is associative. Okay, by the way, these formulas may be easier to comprehend if you, instead of doing this f of, just write the f in this new form. So in evaluating two parameters in this power series, write it as plus sub f. So what this is saying is that z1 plus, so let's define this. So define z1 plus f of z2 to be f of z1, z2, then what the property says, so if this is A and this is B, A just says that z1 plus f of z2 is z2 plus f of z1, and B says that z1 plus f of z2 plus f of z3 equals z1 plus f of z2 plus f of z3. Okay, it's just saying that this addition that we've constructed is associative, it's commutative, and there is another power series I such that I is my inverse. It gives me my additive inverse. It's actually, when I substitute, I get 0. Okay, so this says that z plus the inverse of z is the 0 element. Okay, so this is what it's called a group law. Oops, I didn't mean to do that. A group law without any group elements. And this is, in fact, what we call a formal group. Okay, I'm going to stop here, but in the next video, I'm going to define formal groups starting from here. So now we're going to forget about elliptic curves, but this is the motivation that what we've done is start with an elliptic curve, switch to coordinates around O, around infinity, try to do addition there. Formally, we found power series that give me points on the elliptic curve as just power series solutions, and use those power series solutions to actually, in the case of a local field, find points on the elliptic curve defined over the local field. And once I had those points, at least this sort of like subset of points, x, y, such that x divided by y is in the maximal ideal, for those points, what I did is bring those back to the maximal ideal, bring the addition on the elliptic curve to the maximal ideal, and compute a new series, a power series that gives me how to add just elements of the maximal ideal, forget about the elliptic curve, but now how to add them directly in the maximal ideal without having to do addition on the elliptic curve. And this addition is what you see on the screen. This power series is the power series that gives me the addition. When you have a power series that satisfies, that is the addition that is defined as commutative, it's associative, and there is an inverse for it, then now, again, thinking about it formally as just a power series ring without evaluating in anything, what this is giving me is sort of like a group law, but I don't have any points yet until I actually start evaluating this at things, for example, in the maximal ideal of a local field. Then I can actually compute and construct a group that is attached to this group law. But in the vacuum, this is just a group law without any group elements and will be the basis of what a formal group is. So I only have 5 minutes, so maybe at the risk of making this a very long video, I don't want to just start a new video and just simply define local formal group and stop. So let me just define a formal group, and then we'll stop.
Sorry, Professor, is it all right if I interrupt you before we do that? I'm so sorry if I end up taking up.
No, go ahead.
Okay. I'm a little confused at exactly what object we have spent our time constructing in f of z1, z2. So I understand that it's a formal group law. That part I get. What was all the other stuff we just did in class? I'm pretty sure that all led to constructing the formal group law, but what I'm sort of understanding is that, okay, we did all that construction, but now we're going to completely divorce it from the context in which we constructed it. Am I misunderstanding what we're doing?
No, you're completely right. This is the most confusing chapter in the entire book, because that is what happens. It's a very confusing construction, and then you divorce it completely and just start thinking about formal groups on their own. And then we're going to come back to it in the next chapter. We're actually going to, I will put examples along the way of constructing a formal group, and then how the formal group, once you throw points, so the formal group is just the formal group law. Once you throw some points to it, then I'm going to create a group, which is the group of points on an elliptic curve over QP, for example, and then deduce properties of the elliptic curve over QP out of the general theory of formal groups. But what we've done is what I sort of like mentioned before, that we started, what we wanted to do was to construct a way to just give power series solutions to elliptic curves. Okay, because thinking from the perspective of a complete field, I'm going to be able to evaluate a power series in complete fields when the variable is evaluated at a element of the maximal ideal. Those power series converge because the field is complete. with respect to that ideal. So if I build power series, they are no good over the rational numbers, for example, or over the integers. They're no good to evaluate there, but they are good if I have a power series solution to my elliptic curve. They are good to evaluate at elements of the maximal ideal in the local field. So what we've done is construct solutions in power series and construct a way to think back, instead of having to do all the addition on the elliptic curve itself, think about over the local field what that addition is going to look like directly in the local field, directly in the maximal ideal. You have a, if I have over Q5, I have the number 5 is in the maximal ideal, the number 15 is in the maximal ideal, the number 5 will correspond to a point on the elliptic curve, the number 15 will correspond to a point on the elliptic curve, and I want to know what is 5 plus 15 on the elliptic curve. In the maximal ideal, it's just 5 plus 15 is 20, but in the elliptic curve, is going to be another element of the maximal ideal, maybe, I don't know, 25, or probably not 25, but anyway, some other element of the maximal ideal, that when I send it over with my map is going to correspond to the point that is actually the addition of the point that corresponds to 5 and the point that corresponds to 15 on the elliptic curve. But it's going to be easier to just work directly in the local field with this new sort of like crazy addition that to work on the elliptic curve itself. Does that make sense?
Yeah, that does. That helps a lot. Thank you.
Yeah. So we're going to, for the time being, I'm going to define formal group, and as you said, divorce it from elliptic curves. We're going to prove some things about formal groups, and then they're going to be very useful later on for actual elliptic curves, which is going to come back when we put the points back into the group, and the points are going to be related to the formal group of an elliptic curve. So again, here is the formal definition of a formal group. We'll see it again at the beginning of the next video. Let R be a ring, then a one parameter commutative formal group F, calligraphic F, defined over R is a power series capital F, X, Y, and the power series ring with coefficients in R in two variables, satisfying the following properties. First, the power series, it starts like X plus Y plus terms of degree at least 2. If you go back to the power series we've constructed, I wanted to at least show you this because it is here. You see that the z coordinate of your third point of intersection is minus z1 minus z2 plus higher order stuff. And when you do the inversion, it will change the sign. So my power series does start, my power series capital F in the formal group of an elliptic curve, it does start at z1 plus z2 plus terms of higher order. Okay. B, we want it to be associative. So if I add first y and z and then add x, is the same that if I first add x and y and then add z. Okay, so this is associativity. I did define it to be an abelian formal group, so I do want it to be abelian. So f of xy should be the same that f of yx. It's commutative. Part D is that there is a unique power series in one variable this time, such that f of t it is 0, so that is the existence of an inverse element. And if I add x to 0, I get x. If I add 0 to y, I get y. So there is a 0 element, there's a neutral element. Okay, and we call this f the formal group law of the formal group F. We usually call the pair, so there is the formal group is the pair like this, but there is actually the formal group and the power series that are essentially the same thing. There is some redundancy in the definition. One can show that actually A plus B, so A plus B actually imply D plus E, and I believe if R is, I forget, there are some more conditions on R that I would actually also imply C. So the parts A and B are actually the fundamental properties, but it's nice to just put them all together because then this really resembles what a group looks like. But you see that is a group law without actual points. I'm not telling you what is the set of points or anything. This is just like how to add points. If there were points, this is how you would add them. Okay, so I'm going to stop here, and next time we'll start from here and then just talk about group formal groups in general and some properties about formal groups before we go back to elliptic curves over local fields. All right, I'll stop here.